Hi, this is Dr. Richards with another video. Today, I'm going to cover thermistors and light-dependent resistors, electrical components which rely on semiconductors. I'm going to explain how these components work and how they're used inside circuits. Semiconductors have resistances in the range between conductors and insulators. However, what's even more important is that their resistance isn't necessarily fixed. The components which we'll look at today rely on this variability in resistance, which gives them their functionality. This is best explained if we get into the details, so I'll start with thermistors. These, as the name implies, are resistors, but resistors which depend on temperature. Specifically, we're discussing negative temperature coefficient thermistors, whose resistance decreases as we increase temperature. This is the opposite behaviour to what you might expect. In most materials, the resistance increases as you increase temperature. Think of a filament lamp. As we increase the temperature, the ions in the lamp increase their kinetic energy and oscillate with a larger amplitude, increasing the resistance. However, in a thermistor, we see the opposite behaviour. As we increase the temperature, it causes the resistance to fall. Now, we're not going to cover the exact mathematical relationship today as it's not needed, but I'll say that this relies on an exponential function rather than being inversely proportional, as you may have assumed. The question which is important to answer, however, is why does the resistance decrease with an increase in temperature? Well, the answer lies in the fact that they are made of semiconductors, which have unusual properties. At lower temperatures, semiconductors behave like insulators. That is, they have very few free electrons. This means there are not many charge carriers which are free to contribute to electric current. But as the temperature increases, the number of free charge carriers also increases, which means the resistance falls. There are a couple of ways to think about this, which I hope will be helpful to your understanding. You might recall, for example, the transport equation. I is the current, A is the cross-sectional area, V is the drift velocity of the electrons, and E is the charge of an individual electron. But the important part for now is N, the number of free charge carriers. The current is proportional to the number of free charge carriers. So if we increase this, we also increase the current. Conversely, as the current has increased, the resistance falls. In case this explanation doesn't work for you, another way to think about what's going on is to picture the electrons in the semiconductor. In these devices, the electrons can either be bound to atoms or free to move, i.e., they can be charge carriers. Sometimes we draw a diagram with two bands, the valence band and the conduction band. The valence band represents the electrons which are still bound to atoms, and the conduction band represents the electrons which are free to flow and contribute to current. So, at low temperature, most of the electrons are in the valence band. But as we heat the material, these electrons gain energy and jump from the valence band to the conduction band. These electrons are now free to flow, which means greater current and a decrease in resistance. This picture is especially useful as it also explains the behaviours of LDRs, or light-dependent resistors. Again, as the name implies, LDRs are resistors which respond to light. Specifically, if you increase the intensity of light on the surface of an LDR, the resistance falls. The graph shows a very similar relationship to the one we saw earlier, except now we're increasing the light falling on the component rather than the temperature. The reason this behaviour occurs is also very similar. As light comes in, it's absorbed by the electrons, which move from the valence band to the conduction band. This means there are now more free electrons which are able to contribute to the current. This causes an increase in the current and a decrease in the resistance. However, I'm going to leave it there for today. If you've enjoyed this video, please let me know in the comments. Until next time.